Have you ever thought how submarines get oxygen? This is based on the chemistry of electrolysis. In fact, the electrolysis of water produces oxygen in submarines. In this class, we will learn the laws of electrolysis. You might be familiar with electrolytic cells, right? In an electrolytic cell, a chemical reaction is brought about by an external voltage source. For example, you can see an electrolytic cell here. It consists of two copper electrodes in an aqueous copper sulfate solution. When the external voltage source is on, reduction occurs at cathode, the electrode connected to the negative end of the power supply. At anode, copper metal undergoes oxidation. The copper metal loses two electrons and forms copper 2 plus ion. Thus, copper gets dissolved at anode. And where does it go? Yes, it gets deposited at cathode. This process is called electrolysis, the process by which electricity is passed to a substance to result in a chemical change. Do you know that electrolysis is commercially very important as it is used widely in separating or obtaining pure elements from naturally occurring sources such as ores? Now, can you name the scientist who first summarized the quantitative aspects of electrolysis in his laws? Yes, it was Michael Faraday. Faraday's first law states that the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte. Faraday's second law states that the amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. If m is the mass of an element of E equivalent mass is deposited on the electrode, then by Faraday's second law, you may write m1 divided by E1 is equal to m2 divided by E2. By Faraday's law, the amount of charge passed through the cell Q is determined from the product of current and time. The amount of charge required for the oxidation or reduction depends on the stoichiometry of the electrode reaction. For example, in the reduction of 1 mole of silver, 1 mole of electron is required. As charge on 1 electron is 1.6021 into 10 raised to minus 19 coulombs, the charge on 1 mole of electrons would be Avogadro number into 1.6021 into 10 raised to minus 19 coulomb. This quantity of electricity given by 96487 coulombs per mole is called Faraday. Does this type of electrodes influence the formation of products during electrolysis? Let's see. In this reaction, you can see inert electrodes such as platinum, gold, etc. They act as the source or sink of electrons and do not participate in the chemical reaction. On the other hand, electrodes such as copper or zinc are reactive and it participates in the electrode reaction. The products of electrolysis also depends on the nature of oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. You can see the order of increasing strength of oxidizing agents and increasing strength of reducing agents in this table. Certain kinetically slow electrochemical processes, for example, electrolysis of molten NaCl, requires a higher potential. This is called overpotential. Only if this potential is applied, electrolysis occurs. The products of electrolysis depends on this overpotential value. For example, during the electrolysis of molten NaCl, sodium metal is reduced at cathode and chlorine gas is oxidized at anode. However, in the electrolysis of aqueous sodium chloride solution, the products are sodium hydroxide, chlorine gas and hydrogen gas. Here, at cathode among sodium ions and hydronium ions are reduced preferentially over sodium ions. This is because of the higher standard electrode potential of H plus ions, that is hydronium ions. However, H plus ions are produced by dissociation of water. At the anode, based on the electrode potential values, you may find oxidation of water as the preferred reaction. However, oxidation of water is not kinetically feasible, so chlorine is produced at anode, not oxygen. Note that while considering the concentration effects, standard electrode potentials may be replaced by electrode potentials given by Nernst equation. Now, as we have come to the end of this session, can you predict the products of electrolysis of dilute and concentrated sulfuric acid? With this, I will summarize this video.
Manorama Horizon. Learning made simple.